Alright, so we've talked about different types of distributions, and what we're going to do now is kind of hone in on the normal distribution, because this is, I don't want to say it's the most common, but it's the one that we can kind of do the most with. The normal distribution, if a data set is unimodal and approximately symmetric, remember it doesn't have to be perfectly symmetric, but approximately symmetric, then we call it normally distributed. Normal distributions have the following properties. The normal curve is symmetric about the mean. So what that means is the mean here, the mean falls right in the middle of this distribution. So right in the middle is going to be the mean of the distribution. Alright? Next, the total area under the curve. This is going to be an important concept moving forward. Area under the curve is equal to 1. We can use area under the curve to relate to probabilities, and you'll see how in a little bit. So the total probability we know of a particular of outcomes happening when you take all outcomes into account is going to be equal to 1, and that's directly related to the area under the curve. Alright? This curve also continues in both directions infinitely. Alright, so this actually approaches but never touches that x-axis. Theta's a bunch more around the mean in the middle, and then as we move away from the middle, the data gets the frequencies of the data get less and less, but it continues on in both directions infinitely. To go back up to this, because it's symmetric, we know that 50% of the data is going to be below the mean, and 50% of the data is going to be above the mean. The other piece of this is this next notch right here. This is called the normal distribution curve. If we go up 1 standard deviation, so we add 1 standard deviation to the mean, that takes us to this tick mark right here. If we go up 2 standard deviations, then it takes us to this little mark right here. If we go up 3 standard deviations, then it takes us here. So you can see the area under the curve between the data points that are going to fall in here. There are a lot fewer data points that are going to fall between 2 standard deviations and 3 standard deviations, and even less that are going to fall from 3 standard deviations beyond. Continuing this, if we go down 1 standard deviation from the mean, that takes us to this mark right here. If we go down 2 standard deviations from the mean, it's going to take us to this mark right here. And if we go down 3 standard deviations from the mean, it's going to take us to this mark right here. Alright, so we generally stop at 3 standard deviations. We'll talk about this more, but anything beyond 3 standard deviations is what we would consider an outlier. Again, we'll talk about that more in a little bit. But 50% of the data is going to be below the mean, 50% above the mean, and we can break this down into these particular segments of the normal distribution, like so. So the next concept we want to talk about is this concept of z-scores. A z-score is the z-score of a data value represents the number of standard deviations that it is above or below the mean, and we can calculate it using this formula right here. And if you break down this formula, this is your mean, this is your particular data value, so this is just deviation. Wrong pen there. This is deviation of our particular data value, and we're going to divide that by the average deviation of all the data values. And what that spits out is a z-score. And this z-score is going to represent how many standard deviations above the mean that particular data value follows or falls. Alright, so what we're going to look at is what does our normal distribution look like if we incorporate z-scores into it. So if we incorporate z-scores into this normal distribution, we get what's called the standard normal distribution. These are called, z-scores are also called standard scores. It's a way to take two different distributions and kind of compare apples to apples. So this is the standard normal distribution. So it's still normal, so it's still centered around the mean, but a z-score that falls at the mean is going to have a z-score of 0, or a data point that falls at the mean, because it doesn't deviate from the mean, is going to be 0 by whatever the standard deviation is, which is going to equal 0. So this thing is actually centered at 0. If we go up 1 standard deviation, just like we did in the last slide, and that's going to have a z-score of 1, up 2, z-score of 2, up 3, z-score of 3. If we go below, our z-scores are actually going to become negative. So our standard normal distribution looks like this when we incorporate z-scores. So this is using z-scores to plot. We're plotting z-scores on our normal distribution. All right, so a couple quick examples. We want to calculate the z-score. Here's a scenario. In a survey conducted by the National Center for Health Statistics, the mean height of women in the U.S. ages 20 to 29 was 64 inches. So that's a mu equal to 64 with a standard deviation of 3. This is population data for this particular age bracket of women. So sigma would equal 3. So what we want to do is we want to find the z-score of a woman that's 60 inches tall, and we just want to use this particular formula. So in this case, our x is 60, and then our mean is 64. Our standard deviation is 3. So the z-score of a woman that's 60 inches tall is going to be our data point minus the mean over the standard deviation. All right, because this height is below the average, we should expect our z-score to be negative, and in fact it will be. So we would have negative 4 over 3, which equals about 1.33 for our z-score. So there's our z-score for a woman that is 60 inches tall. She would be 1.33 standard deviations below the mean. The sign is going to indicate whether it's above or below the mean. Next example, find the z-score of a woman that's 64 inches tall. So again, our x here is 64. We're going to find the z-score of a woman that's 64 inches tall. So z sub 64 is going to be our data point minus the mean over the standard deviation is 3. And because this data point is right at the mean, we get a z-score of 0, which should be expected. It doesn't deviate at all from the mean, so it is 0 standard deviations above or below the mean. Last one, find the z-score of a woman that's 75 inches tall. So x equals 75. Find the z-score for this particular height. Take our data value, subtract 64 from it, and divide it by the standard deviation. The z-score of a woman that's 75 inches tall is going to be 11/3, or 3.67. So this one would be 3.67 standard deviations above the mean, because our z-score has a positive value. And like we talked about before, if you are greater than 3 standard deviations above the mean, we would consider you an outlier, so we would make note of that. Where this is really useful is if a data set is normally distributed, we can actually calculate the percentage of data that's going to fall within particular data values. And so this empirical rule is what allows us to do that. So the empirical rule says that if a data set's approximately normal, then data points, the percentages of data points are going to follow this particular chart. So what we notice is within one standard deviation, and that's the terminology, within one standard deviation, we have 34 plus 34 is 68% of the data. All right, so 68% of the data, so a little over 2/3 of the data is going to fall within one standard deviation if we know that that data set is normal. Within 2 standard deviations of the mean, so we're going to bump out now to 2 standard deviations away. We tack on another 13.5 and 13.5, so that's another 27. That takes us up to 95% of the data. So if it's normally distributed, 95% of the data points are going to fall within 2 standard deviations of the mean. We bump out to 3 standard deviations. So within 3 standard deviations, we're going to tack on another 2.35% on each side, so that's 4.7. So that gets us to 99.7% of the data is going to fall within 3 standard deviations. So you go back to that whole outlier thing, and we talked about anything outside of 3 standard deviations. Well, that means that if you relate it to what this empirical rule says, that means that 0.3%, or 3 out of every 1,000 people, are going to be outside of 3 standard deviations. So those are very unusual data points. So if you're talking about heights, you're talking about somebody that's really tall or really short, they would be considered outliers. So outside 3 standard deviations are considered outliers, because it's so improbable that you get someone or a data point that's that far away from the mean. Quick example on how to use this. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the U.S. was 64 inches with a sample of 3. So quick sketch of the distribution. We know that centered in the middle is going to be 64. We go up 1 standard deviation, it's 67. 2, it's 70. Up 3 standard deviations, it's 73. And we also go down. Three standard deviations, and this is going to give us a quick snapshot of what's going to happen. So if you use that empirical rule, you should be able to kind of relate the amount of data that's going to fall within particular boundaries. So use the empirical rule to estimate the percent of women whose heights are between 64 and 70 inches. So between 64 and 70 inches is going to be this. We know that that is 34%, so 0.34 is going to fall within here, and another 0.135 is going to fall within 67 to 70. So we can actually find the probability, or the amount of data, or the amount of women that are going to fall, the percentage of women that are going to fall between these 2 heights. And this one in particular would give us about 47.5% of women are going to fall between 64 inches and 70 inches tall. One more example, use the empirical rule to estimate the percent of women whose heights are between 58 and 67. So go back up here, 58 is right here. We know that there is 0.135. 13.5% of women that are going to fall within there. 34% of women are going to fall within these 2. What we're interested in here is the percentage of women that are going to fall within 58 to 67 inches. So we would add 13.5%, 34%, and another 34%. And add that together, you're going to get 68, 71.5% of women will fall between those heights.